Since the electric field obeys the principle of superposition, so does the potential. The potential of many charges is just the sum of the potential of each individual charge. But here's the beauty. Electric potential is a scalar. Adding them is easy. No messing around with vectors and components and such. Just add them like numbers. However, be sure that the potentials you use all have the same reference point, that they all agree where V equals 0. This can be an issue if you're using a potential computed by someone else, or if you're using different parts that you're assembling or something like that. And it's not a big deal. You just shift some of them so they're all on the same reference point, but just make sure you do. All right. Remember that an electric dipole is a positive charge separated by some equal negative charge by some distance d, where we say the dipole is charged plus q. We know that there's a minus q out here, and so the net charge is 0. But we've referred to it as the positive charge for concreteness. And since we're adding, basically, if we take a point like this, and we say we're at, say, this point with an R1 and an R2, we would say that the actual potential is 1 over 4 pi epsilon naught q over R1 plus 1 over 4 pi epsilon naught minus q over R2, when we would just add them up. The way this looks as drawn here, our contour map looks like this, where this is usually considered to be, well, this is 0. If these have the usual potentials, notice that on the midline between them, these two things would have equal R1 to R2, and they'd be 0. So this is a 0 line, the same as at infinity. If we look at the elevation graph, we see sort of an interesting thing, which is that we've got sort of this mountain and this inverse mountain, this little pit or whatever. And again, we can see how the contours map out. This, of course, is exactly why it's a dipole. It has 2 poles, 1 plus, 1 minus, but other than that, 2 poles. And there's a lot going on. You can see that since the electric field is the slope, it's kind of complicated. Dipole fields are not simple. All right, so looking at the midpoint between these two equal but opposite charges, which of these things must be true? Well, we know there's an electric field that flows from the positive to the negative. Actually, the electric field looks sort of like this. In a way, and in. So we know there is an electric field, so it can't be any of these 3. And as we talked before, if we're equidistant between the two, then the distance is the same, but the contributions to the potentials are opposite because the charges are opposite. So we have no potential, so we are in this region anyway. And the electric field flows from positive towards negative, so it must be that one. All right, at which point or points is the electric potential 0? And notice this is not really a dipole because the charges are not equal, so we can't just invoke what we just did. The charge on the right, well, I guess we can say the total potential is 1 over 4 pi epsilon naught 2q over some distance, we'll say 1, where I'm going to pick any one of them. That's the distance R1. And then we'll have 1 over 4 pi epsilon naught minus q over R2, where R2 is the distance to some other point. So here I'm looking at point B, but we look at any of them. And we can see that for this to be 0, V equals 0 implies that 2 over R1 equals 1 over R2. That it must be twice as far from the 2 positive charges as it is from the point is from the negative charge. So we can see that that definitely includes point C, right? Because that's 2 units to that 1. Oops, well, that's bad. 2 units to 1 unit. But, and this is a little maybe shocking, also, that's 3 units, and that is 6. So that also satisfies. So we also get D. C and D are our answers, which means technically, really, I guess our answer is E, more than one place. All right, an electron is momentarily at rest between the two plates of a capacitor, and the various capacitors are shown here with their voltage differences and their separations. It says draw a blue circle around the case or cases where electric force has the greatest magnitude, and a red circle around the cases where it has the least. So we have to remember how to get the electric field. And the electric field, remember, is minus the change in voltage over the change in distance. Strictly, really, it's the slope, so dV dx. And if we look at this, we have 100 volts over 2 centimeters. That's 50 volts per centimeter. Here we have 100 volts per centimeter. This is also 50 volts per centimeter. And this is 100 volts per centimeter. So these are the greatest. And these happen to equally be the least. And we see that the condition of the electron really doesn't matter. As long as it's between the plates, it doesn't matter where it is between the plates. And it doesn't matter that it's at rest. All right, these plates have been charged to create a uniform electric field of 30 newtons per coulomb. We have a bunch of points marked, and we want to say, draw a blue circle around the cases with the greatest potential difference and a red circle around the cases with the least. In this case, unlike many of these problems, we are not asked for a magnitude, so we have to keep in track of which are positives and which are negatives. So it might just be easiest to figure out what the actual voltage difference is. And the voltage difference, remember, will be inverting what we just had, that delta V is minus E delta X. So from M to N, right, the electric field is constant, so we really care about the greatest distances. Here we have that it, from M to N, it decreases. And in fact, we have something like minus 30 newtons per coulomb times 3 centimeters. And that turns out to be minus 0.09. And going from N to O is actually the same thing, because the field is constant. And then kind of interestingly, going from P to N, again, this is the only bit that matters because the field only varies in the horizontal. So this is actually going to also be minus 0.09. Going from P to M, as in Matilda, well, they're each the same distance from the plates. So there's actually no potential difference between those 2 points. And then going from P to O is the same as going from M to O, which would have been minus 0.18. And then going from N to M, I'm climbing the potential grid, so I get plus 0.09. So we can see clearly the largest one is this, and the smallest one is this.